Okay, now since we've now got the recurrence equation of the total running time of the merge sorts in such a form in the lower right corner here, okay? And in order to solve this recurrence form, we need to first make some further simplification. Okay, so we rewrite the recurrence bits, okay? We introduce some constant terms because we want to get rid of the big theta notation. Because big theta of 1 indicates a constant term, so we use C to indicate a constant, okay? And the big theta of n indicates a linear regression a linear model, so we basically use C times n here, okay? So it's a rewrite of the previous recurrence equation in the previous slide, but we'll basically stick with this for now, okay? So here's where the trick happens, okay? So we can rewrite the recurrence equation in such a form, and we first focus on these parts, okay? T of n equals 2 times T of n over 2 plus Cn. So there are 3 terms, and we can visualize it into 3 parts, place them into this triangle relationship. So we put the Cn here, which is a constant term, which is a linear term, and this Cn is the cost of doing the merge procedure, right? And the left branch is one subproblem, the cost of solving the left subproblem. And the right part is the cost of solving the right subproblem. So that's one split, one divide, right? And then we need to think of this recursively, because here, the problem on the left and the problem on the right, they can be further splitted, right? I can add a branch here and a branch here, right? So let's further divide the term into branches, and we will generate something like a tree plots, okay? So how do we get the C times n over 2? We simply by substituting the n over 2 into the recurrence equation here. If we let n be n over 2, then here it becomes n over 4. And here it becomes C times n over 2. So this is why we have C times n times 2 here. It becomes a new node, okay? And the same value for here. And the sub-problem become n over 4 size, the size of n over 4, okay? And that's the problem of solving the even smaller sub-problems, okay? So in theory, we can further split all these terms, all these nodes in the tree to get a longer and longer, taller and taller trees until the point that the subproblems are small enough that there's no way to further divide them, okay? Right, in theory, these dividing steps can going on, okay? And these tree plots will give us some intuition of how to solve to get an analytical solution to the running time T of n. Okay, so let's assume that at some points we hit the bottom and all the subproblems, they are the smallest and they can no longer be solved. And the recurrence equation says that in the smallest case, the time for solving it is C, right? So we can simply put a row of C at the bottom, right? And these are the smallest subproblems, okay? So now everything in these tree plots, if we add them up together, they will be the total cost of solving the merge sort problem, of solving the original problem, right? So one way of solving this is that we view each level of the tree individually. So the first level, we've got Cn. There's nothing else. And the second column, there are two parts. There's one Cn over 2 and the second Cn over 2. So together, they contribute Cn as well. Then the third level, okay, we have 4 times Cn over 4, okay, because we want to kind of want to add them up, right? Add all these components up. We've got also Cn. So we just can't help wonder that whether it is true that each level they have the same summation Cn, okay? So we can prove it later that indeed the summation for each layer is Cn, but we will not do that here. We just take this as a fact, okay? We take this as a fact that all the upper levels, all the non-leaf node levels, they sum up to C times n, okay? And all the bottom levels, they all times up to C, also sums up to C times n, okay? Because it is a merge sort problems and the original input has n numbers. So if we split it into the smallest sub problems that each has only one element in it, there must be n of such problems, okay? That's why we also have Cn in the bottom level. All right, that makes things much easier, okay? So, and also we know the number of levels. We can do some calculation by knowing that the number of levels is the logarithm of n plus 1. Okay, so how do we get that number is also a bit tricky. Basically, we need to observe the fact that for level I, and the I starts with 0. Okay, so we call the level here, the level at the root here, the I equals 0. Okay, and for this level, the I equals 1. So for I equals 0, the number in the node is C times n over 2 to the power of I. Okay, so for this level, 2 to the power of 0 is 1. So then sum is, so the number in the node is C times n. That's correct, right? And for this level, I equals 1, then it becomes C times n divided by 2, which is also true, okay? So when it reaches some certain level I, the number in the node must be C times n divided by 2 over I, 2 to the power of I, okay? So when it reaches the lowest level, okay, when it reaches lowest level, it is C, right? And by solving this equation, right, we can cross C out, and we've got this, and simply we can solve I. Okay, so for the last layer, for the last row or last level, I equals logarithm of n. Okay, the base of logarithm is 2. Okay, so basically we have I from 0 to 1, 2 until logarithm of n, and this is a obvious answer that the total number of level is logarithm of n plus 1. Okay, so the total running time is, okay, so we need to manipulate, we need to use another fact that the summation for each level doesn't change. Okay, it doesn't matter which level you are. Okay, the summation is C times n, always C times n, no matter which level you are. And we know that there are that many levels, and each level is that summation. So the total running time is Cn times logarithm of n plus Cn. So bingo, we've got the solution of T of n. Okay. So now one more important step is that we want to notice the fact that this is a higher order term. N times the logarithm of n is a higher order term than Cn. Cn is a linear function, and the fact that Cn times log of n is higher order means that we can ignore this term. So the total running time is determined by the highest order term, which is n times log n. And that's why we can use big theta of n times log n to describe the running time of merge sort. Okay, so that's it for the running time analysis for merge sorts. And now let's look back and compare it with the insertion sorts. Insertion sorts, the average running time is big theta of n squared, right? We did that analysis because in the worst case, the while loop need to compare with all the elements before the key value. So that's why the average case is also the same level, the same running time. And the merge sorts, we have that, know that's it's big theta of n times n. And the square functions, quadratic function grows faster than n times log of n. So merge sort runs much faster, especially when n is large enough, the difference can be very salient, okay? And these facts also tells that n should go in faster than logarithm of n, right? Logarithm of n is a curve that never reaches the linear line, straight line. All right, so as a recap of all the contents for this lecture, which is to get started with sorting problem, we introduced the pseudocode, insertion sort, and the merge sorts. And the most important part is that we analyze the running time for these two algorithms, and we have a brief idea of the big theta notation to describe the running time for the two algorithms. And we know, kind of know that the second merge sort algorithm has a better running time because this function, n times logarithm of n, grows slower than this function. And in the next lecture, we're gonna formally introduce the concept of growth of functions, so that we'll know how formally we define which function grows faster than the other. And that's it for the course today. Thank you.